In this demonstration, you'll learn how to set up a steady-state thermal electric conduction simulation to gauge the performance of a thermal electric cooler. To start, I'll select the thermal template from the study panel. I'll select the option to define new geometry. I'm going to add the electric conduction simulation physics as well, and accept the default selection for the options list so that contacts in the interface of the bodies are detected automatically. I will then apply the template and create the simulation process. AIM has automatically created the physics solution process using default settings for the geometry, meshing, physics, and results, everything I need for my analysis. The first thing that I'm asked to do is define my geometry, so I'll select the geometry task. There, I'll import a geometry file. I'll select the file for the thermal electric cooler. AIM loads the geometry and sets up a default mesh. The red exclamation mark here tells me that the physics task needs more information to complete the simulation. I'll click it to go into the physics task. You can see that a lot of defaults have already been set up for me. AIM has also created an interface generator, so contacts will be generated when this task is updated. While a material has been assigned automatically to the geometry, I want to change the material to copper for the copper plate, so I click this default material assignment. I need to select bodies rather than faces, so I use the body selection filter. Then I select the copper plates and semiconductor pellet, and replace the default location. Now I change the material to copper. Density, specific heat capacity, thermal conductivity, and isotropic resistivity are already defined. I'm done with copper, but I still need to define the material for these two semiconductors. First, I'll assign the material for this N-type semiconductor. I select it in the geometry, and right-click to add a new material. I'll name it N-type semiconductor. Now I need to add my material properties. First, I'll add isotropic resistivity and set the value. I finished defining the material properties by adding isotropic Seebeck coefficient and isotropic thermal conductivity. You can see the values here. I'll repeat this process and assign material properties for the P-type semiconductor. You can see it defined here. So, I have set 3 material assignments: copper, N-type semiconductor, and P-type semiconductor. I am now going to add some boundary conditions. First, I'll set a temperature. I change the selection filter to faces, and select the bottom faces of the copper strap. Then I right-click to add a temperature, and set the temperature. This demonstrates thermal electric cooling. Next, I'll ground the end of this P-type semiconductor. I select the end face, and right-click to add a voltage. I'll set this to 0 to indicate it's grounded. I will also set a current on the input electric terminal and a rate of heat flow to the copper strap. So, I've set up 4 boundary conditions: temperature, voltage, current, and heat flow. Now I'll solve the physics solution task. Because the meshing task was also ready, it will be automatically updated first. Everything's finished now, so I can view my results. I'll click on the Results task, and then Evaluate. The template has already inserted several results by default. One contour result is temperature. This simulation results in a cold junction. You can see that the face with the heat flux has a temperature close to 0. Next, I can view the electric potential result. You can see that the current passes from the input terminal to the ground, from higher voltage to lower voltage as expected. This concludes this demonstration of an end-to-end basic steady-state thermal electric conduction simulation in AIM.